My name is Tomcin. I'm a visiting scholar from Germany, and I'm going to do the next 3 lectures, as Ladislav probably told you. And it's about rigid body theory. So, that's my name. And today I'm going to do unconstrained rigid body motion. So we are basically looking at the motion of a single rigid body and just how it moves over time. Under the influence of external forces like gravity and maybe if we have time we will come to springs as well. Okay, so as I think Ladislav also told you a little bit of why rigid bodies are so popular, especially in real-time applications like games. So, for example, you probably know that like every first-person shooter now has some sort of rigid body simulation in it. And the reason for the simplicity is that a rigid body has only 6 degrees of freedom, meaning that you have 3 translational degrees of freedom, meaning you just need x, y, z to determine its position. And then you have 3 rotational degrees of freedom, which is, well, you can basically describe the orientation with only 3 angles. So for example, airplanes have this typical jaw, pitch, and roll angle. But as you know by now, it is usually advantageous to use rotation matrices or quaternions to define the orientation of a rigid body. Okay, so incidentally, so what's the number of degrees of freedom for a 2D rigid body? You only need 2 translational coordinates, x and y, and then only 1 angle, right? So, for example, an idealized car on a parking space or something could be described by just 3 parameters. Okay, so of course, there are rigid bodies. You can also put constraints on the rigid bodies. For example, a door is still kind of a 3D object, but it only has 1 degree of freedom. But in this lecture, we are only concerned with unconstrained motion for now. So we are not looking at any articulation, joints, or hinges, or something like that. Okay, so let's maybe think of a rigid body as just a collection of points. So we have a rigid body, and we can think of it as, or approximate it by just some particles, where each particle has a mass, mi, and we've got n particles. So the mass of our rigid body would then be denoted by capital M, and that's just the sum over all of our n particles. So we sum up the individual masses, right? Okay, now we should also define a local coordinate system for our rigid body. So, okay, let's think of for example, a rectangle rigid body, and now it's good to first compute the center of mass of this rigid body. Now, of course, for a symmetrical body like this, it's pretty simple. It would just be the center, and now in our global coordinate system, we would then describe the position of the rigid body with respect to its center of mass. So this is the position, x. Now, of course, in the beginning, your rigid body might not be aligned to the center of mass, so you somehow need to compute it. And well, for this, for our, well, if we think of it as a collection of particles, it would be just, the center of mass is 1 over m. Oh well, sorry, that's the German one. I tried to with the American one.
Okay, we're used to it.
Okay, yeah, I know. Like, to you, this must look like a 7 probably, but yeah, probably I forget it anyway. So this is a 1 for me. Okay, and then if we denote the positions of these particles as Ri, then it would just be 1 over m times mi Ri. Now, of course, there's also a continuous version of these formulas. And then you don't have sums, but integrals. So maybe I'll just write it down for these two. So the mass would be, let's see, would be the integral over the volume of the body, and so rho is the density, which is just mass per volume, times, well, so we integrate over the volume basically, the density. And of course, usually we can assume the density of such a rigid body to be constant inside, and then this would just be rho times the volume of the body, right? Okay, and for this formula, there's also this vector.
Sorry, what was
R?
Yeah.
That's the position of such a particle. Okay. So here, just in global coordinates, so x would be, let's see, 1 over m times, now this is a vector, so we have 3 integrals. And now this is like the x component of R integrated over the volume, then the y component integrated over the volume, and the z component. But anyway, let's maybe stick with the particle version, because I don't know, it's kind of simpler to derive everything. I'm not sure like how often you use integrals. So yeah, let's stick with the particle version.
I think in those integrals you still have to multiply by density by rho.
Oh right, of course, I forgot. Right. So, I mean, if it's constant, we can just pull it out of the integral, and then it's, yeah, it's right. All right. Now, so let's define a local coordinate system, where the center of mass of the body is in the origin. And now, if we have some particle position, then with respect to this local coordinate system, we call it R0I, and in global coordinates, as we already defined it, it's Ri. Right? And so to transform between the local and the global coordinate system, so the global particle position is just the center of gravity or the position of the rigid body, x, plus its orientation times the local coordinate. And so here in this lecture I'll mainly use rotation matrices to describe the orientation for reasons of simplicity. Alright, so what's the advantage of using the center of mass for this local coordinate system? Now, if you think of a rigid body that just freely moves and rotates through space, then if you use a random point to denote the position of the rigid body, then of course if there are no forces acting on the body and the body rotates somehow, then this this would kind of move on some spirally path, right? The position. But if we use the center of mass, then it just moves on a line. So it basically decouples the translational degrees of freedom from the rotational degrees of freedom. And this simplifies a lot of things. So if you have some random mesh given, you should first make sure that you somehow take care of this by moving all the vertices so that the origin of the local coordinate system coincides with the center of mass. Okay, so then let's maybe first look at the translational degrees of freedom. And that's actually quite simple because you can think of it actually as just a particle. So for example, what's the linear momentum then? Well, it's denoted by capital P. Then it's just the body's mass times its velocity. Right, and the momentum is also a vector. So what about forces then? How do we get to forces? Well, basically we just derive both sides by time, and then we get the linear change, the change in linear momentum is then just the force, basically acting on the center of gravity of the body. So this is just the time derivative. Now the mass is constant, and the time derivative of the velocity is just the acceleration. Okay, so if we have, for example, gravity, then just since we chose the center of mass for our local coordinate system, this is just, well, the gravity just acts on the position without having any effect on the angular motion. Okay. So, I mean, you've probably seen this, F equals ma, it's quite famous. So, how do we compute the motion for this? Now this is a second order differential equation because A is the second derivative of position. That means that we, for every item, we need to provide two things, and that's the position and the velocity. So maybe let's reduce it to a system of first differential equations first. This can be done by just the time derivative of the velocity, which is just the acceleration, right? Is the force divided by mass. Force divided by mass. And then the position, x by dt, is just the velocity. Well, of course, this depends on time. Right, so this is our system that we want to solve. And to do this, we don't do it analytically, but we want to discretize in time. Meaning, well, first let's put in integral notation. So we can just formally basically put the dt to the other side for both equations, and then put an integral around it. So and now we integrate this for some small time period. That's our time step. So let's integrate it from t0 to t1. And that's, well, let's do the same for this. Now we do an approximation, simplifying assumption that the force is constant during this time interval, and also the velocity. So this gives us the simplest time integration scheme called the explicit Euler, and so this integral just becomes v1, so our new velocity minus v0, and the right hand side is our force at the beginning, the time step, times t1 minus t0, and well, that's what we just, sorry. I guess this thing is in the way. And this is just our time step that we call h. And, well, same for the other one. Okay, so yeah, that's all there is basically for the translational motion. So of course, well, you put the v0 and x0 to the other side, and then you can simply compute the new velocity and position of the body. With these two formulas. Okay. And well, of course, if we start the simulation, we also need to provide some initial position and an initial velocity for the body. Okay, but then, yeah, what about the angular motion then? Well, it's a bit more involved, but also quite similar in some ways to the translational motion. So I think I need to write it. Okay, so instead of position and velocity for the angular motion, we have the rotation matrix R, which is the orientation of the body, and the angular velocity omega. So orientation or angular position, it's sometimes called. Our rotation matrix. I think it's like the space is called SO3, right? I think you had that. I think Ladislav told you about that. The angular velocity is a vector, omega t. So, like, what does this vector mean? That's the question. And so its length determines the angle per time, and the axis, like the direction of omega, determines the axis of the rotation. Then, yeah, let me draw a little picture for that. So suppose we have that's omega, our angular velocity, and then we have some point P. Now, if this angular velocity stays constant, this point will just move on a circle around this axis, and this circle is orthogonal to this axis, so we can decompose this this point into two components, A plus B. So this is A. This is B. And now, what's the time derivative of P then, or the velocity of this point? So it's somehow on the tangent of this circle, right? So it goes somewhere in this direction. Let's call it P naught. And now the norm of the angular velocity, that's the angle per time, and of course that's like if B is 1, then this would just be the velocity of the point, right? Or the speed, rather. So just the scalar value. but as this radius, like for example, if we double the radius b, then the velocity will be twice as much. If we half it, then it will be half as much. This is just by definition. So we multiply it with b, and that's just the scalar value, this b. And now what about the direction? Well, that's, as we can see, it's orthogonal to omega and b. So, yeah, that's just the cross product of omega and b. And we also normalize it. So, it's got the length 1. So far, so good. Okay, now we can simplify this expression. So let me just first add something on top at the numerator. Omega cross A. Now, what's omega cross A? Right, it's 0, so I haven't really changed anything, but the reason why I did that is just because, you know, the cross product is a linear operation, so the law of association holds, and this is just omega cross A plus B, so this becomes omega cross P. And now what about this? Now the norm of a cross product, there's this formula that this is just the sine of the angle between omega and B. Omega and B. And the product of the individual norms. Right. And well, since B and omega are at a 90-degree angle, the sine of 90 degrees is 1. So this falls out, and this cancels out as well. So it's just omega cross P. Okay, so now what about some general point on a rigid body? What's its velocity? Let's just call it R, as before. Well, then, just intuitively, you might see that actually it's we also need to account for the velocity of the body, which just gets added to the velocity of the point. So it's the velocity of the body plus omega cross, and now we need to be careful. We can't just use our local coordinate r, but instead we need to transform it to global coordinates. So we multiply it by the orientation matrix. And let's maybe call this, let's give this a name, R dash. So this is the same as So wait. R minus x. All right. So now, what about the time derivative of our orientation matrix? Now, it's surely not as simple as for the position and velocity, since I mean the time derivative of r is certainly not just simply omega, right? Because I mean this is a matrix and this is a vector, so there must be somehow more to it. And as you remember, our rotation matrix consists of 3 columns. These columns are just the coordinate axis of our local coordinate system of the rigid body. So it's our x of t. So these are just the normalized coordinate axes that are orthogonal to each other. Oops. And now thinking of this picture, these coordinate axes are basically just rotated by omega in the same way. So the time derivative is just the cross product omega cross Rx omega cross Ry omega cross Rz. But there's a nicer way of writing this, and indeed, like this omega cross is, as I said earlier, a linear operation. So there's a matrix that can be used to do this operation, and this way we call it omega star. We can just multiply it onto the matrix R. Now, what does this matrix look like? It's actually, well, it just does what the cross product does, and so it looks like this. Minus omega 1, omega 2, minus omega 3, and then it's skew symmetric, meaning that it's symmetric, but the sign changes.
What is Rx, Ry, and Rz?
Fun?
Rx, Ry, and Rz columns of matrix R.
Right. These are the I omitted the time dependence here. Just
yeah, but what are Rx, Ry, and Rz?
well, these are the coordinate axes. So if we have our body, this is the global coordinate system, this is the local coordinate system, then basically it's those normalized vectors of the coordinate axes.
Okay. Right.
In global coordinates, so, right? So it's not just 1, 0, 0, 1, but of course it's rotated. Okay, and it's easy to verify that like multiplying this matrix onto a vector is the same as just using the cross product omega cross the vector. That's exactly what it does. Okay, so that's our time derivative. So now we have a relation between the orientation of the body and the angular velocity. But now, what about the mass? Like, is there something? I mean, for translational motion, the mass is just a scalar constant. So what about the orientational analog of mass, right? Now for that, to derive this, this is called Inertia Tensor, or moment of inertia. And to derive it, we have to look at the kinetic energy of a rigid body. Okay, so the kinetic energy of one particle is just 1/2 times mi ri, right? If we think of our rigid body again as a collection of particles, and the total kinetic energy of our rigid body is then just well, we just need to wait. I made a mistake. Of course, it's not r, but it's the velocity of each particle. So let's call it r dot as before. And then squared, right? So with square we mean just the dot product of itself. And to get the kinetic energy of the whole rigid body, we just sum over all the particles. Okay, now let's put in the equation we derived previously for Ri dot, which gives us, so maybe I just write it here again. So that's force V, velocity of the particle plus the angular velocity of our rigid body cross R I dash V. And this was just R minus X of T. And well, if we put this in, then we get the following expression. By this I mean the velocity of our rigid body, not the velocity of the particle, obviously. So that's this, and then the last term Okay, so let's simplify this. So we can, this is just the total mass, right? And since V doesn't depend on this index, we can just pull it out. So it's 1/2 n times V squared. So this is just the translational kinetic energy. And then, now what about this? So there is a relation for a cross product like that, which I write here. We've got some product A cross B, scalar product with C, and this can also be written as C cross A times B. So you can kind of switch things around. And in the same way, we can, or in the same way, we can do it with this. And then this becomes V cross omega times the sum So, and what's this? The sum over mi ri dash. Well, this is just the 0, right? Because ri dash is like for ri dash equals 0, we are at the center of gravity, and like so it all cancels out. So the whole thing is just 0, falls out. And this part, can this be simplified? No, not really. And this is the rotational kinetic energy of our body. All right, so where am I going with this? So now, of course, we need to concentrate on the rotational part to get to this inertia tensor. Right, so there's some other identity for a cross product like this, and so if you have something like A cross B squared, and this can be written as A squared B squared. Again, squared is just the dot product with itself, minus the dot product A and B. So this is just a nice identity. I don't want to prove it to you now, but it's not that difficult to verify, just with some simple examples. All right, so what's the time? Okay, so then our translational, our rotational kinetic energy. This. Okay, now let's write this in a different way, with more summation symbols. So first we sum from 1 to 3 over k, and now this first part, if you think about it, it's well, I just write it down. It's the kth component of omega squared times the kth component of Ri squared. Oh no, wait. Times the vector Ri dash squared. That's right. Minus, and now we use a double sum from J. And this right part, now if you think about this one, it's basically, we have 3 summons times the 3 summons n, right? So it's basically a little bit like a binomial formula. And this is just omega j r ri j. I mean, ri is a vector, so this is just the jth component of ri.
Do you have 2 k's, or they take other completely separate? Yeah. Maybe.
Well, I mean, it takes some thinking about it, but if you just write out what this is, it becomes clear that this is actually true. I mean, yeah. And now, what we want to do now is just, now here we have 2 separate sums, but we want to put it into like a common summation symbol. So what we do is, this can be written as also as a double sum. I'll tell you in a moment what that is. So now delta ij is called the Kronecker delta, and it's simply delta J, well, Jk is 1 if J is equal to K, and 0 if J is not equal to K. So now we did this to basically be able to interchange, to swap these summation symbols, which is a totally legal thing to do in this case. So this becomes 1/2. Here we have this double sum that we abbreviated like this. So these are two sums. And now we sum over the particles. Okay, and now so this part is the J-K component of our inertia tensor. And in fact, like what's written here is basically omega transposed times the inertia tensor, well, 1/2 times omega. So this is a scalar again, and so maybe just to clarify things a little, let me write out this inertia tensor. Ri2 squared plus Ri3 squared. This is Ri1 squared plus Ri3 squared. And Ri2 squared. Oh, 1. Well, anyway. Plus Ri2 squared. And here, these entries we've got Ri1, Ri2, minus Ri1, Ri3, minus Ri2, Ri3. And the whole thing is symmetric, so I don't bother writing down the other part. Okay, so now these R vectors. Just remember, it comes from this Ri dash. So actually, since Ri dash depends on time. Remember, it's basically the rotation matrix times the position in the local frame. So our whole inertia tensor depends on time. So you see that kind of complicates things a little, because in contrast to the mass for the translational motion, the inertia tensor is a tensor, right? And it also depends on time. So what's up with this time dependence? Well, there's a so if we there's a way to reformulate this tensor as the orientation of our body times a constant inertia tensor with respect to the local coordinate system. Am I outside of the screen? Not quite. Times rotation matrix transpose. Oh, and let's call this I body. Okay, so now what does this inertia tensor mean? Just intuitively. We all know what mass is, but maybe it's not as clear for the inertia tensor. Right, so this is a perfectly good rigid body, right? My mobile phone. And now this inertia tensor is somehow related to the angular motion. And now if we have a look like how such a body rotates, we see that it has like for this simple cuboid, it basically has 3 axes, like this, and this axis. So 3 orthogonal axes and 3 related principal moments of inertia. So what does this mean? Well, if we look at the angular momentum of a body, which we call capital L, this is, I mean, like for the linear momentum, it was just m times the velocity, but here it's the inertia tensor times the angular velocity. So it's pretty much the same formula, just the angular version. And now we see that the angular velocity does not necessarily need to be parallel to the angular momentum, right? So what's usually conserved is the angular momentum, but the angular velocity might change. So if we just toss it up like that, you see that actually it kind of, like the axis of the angular velocity kind of rotates in a cone around this angular momentum. So, however, if we choose one of the axes as the initial rotation, then we can see that it kind of, well, it's difficult to do it exactly, but if I would be able to exactly give it a push so it rotates around this principal moment of inertia, it would just be completely parallel in this case. And also, like for the other axis, so this was the smallest principal moment of inertia, and this is the biggest one. So we can also rotate it like this, and you can see that the angular velocity stays the same, and actually it points for this case as well in the same direction as the angular momentum. And now there's an interesting fact. If we use the middle axis, I mean, let's just try to rotate it like that. If you try to do that, you might notice that actually it's somehow, it always does flip every now and then. So somehow it's not stable, this motion about the middle principal moment of inertia. I mean, you would have to give it a really accurate push around this axis for it to stay at least like a couple of seconds around this axis. Okay, and for all other cases, like if I do it like that, then usually this angular velocity rotates in a cone around this angular momentum. Now, of course, unfortunately, I had to deal with gravity, so there's only a short time to look at it. But I hope you get the idea. And so, I mean, we used a preferred frame that is like reference, corresponding to the center of mass of the rigid body for the translational motion. Now, actually for the orientation, there's also preferred frame. So like how to choose these coordinate axes. And that's, you don't need to do it, but if you choose as this frame the principal axis of inertia, then actually the nice thing would be that this body inertia tensor, which is constant, that would just be a diagonal matrix with all the principal moments of inertia on the diagonal, which is, by the way, also just the diagonalization or eigenvalue decomposition of the time-dependent inertia. Okay. So how much time do we have left? Still maybe around 20 minutes, right? Okay. Yeah, right. So let's do the time integration for the angular motion. I should maybe wipe it away again. Okay, so let me write down the angular momentum again. Okay, so now we want to get to the F equals ma for the angular motion, and that can be done also by deriving both sides by time. And now the time derivative of the angular momentum. That's just the torque or moment. So this is kind of the angular version of the force. We denote it by tau. And then this is equal to, well, you might think it's just I of t times, and then the angular acceleration, let's call it sigma of t. So this is just the time derivative of omega. However, since this tensor depends on time, of course, we need to also derive I by time, right? So just, you probably know how to do this. So we also need to do the time derivative of I times omega, right? So E by dt, and well, let me already write it out. Times omega. So now, well, we know what the time derivative of R is, right? We derived it earlier. That was like this cross product matrix omega star times R. So this is, well, let me just omit the time dependencies for a moment. R I body R transposed plus R times I body and now omega star times R transposed omega, right? Now, how do we transpose this product? Well, the rule is just we need to switch the orders and transpose both. So this would be R transposed plus R transposed. And since it's Q-symmetric, this would just be negative. This transposition just negates omega star. But anyway, if we factor it out, we see that actually there's some omega star omega appearing here. So the cross product of omega with itself, and of course that's just 0. So so this term falls away, and the whole thing becomes sigma t plus this again is our original I, inertia tensor. So the whole thing is just omega of t cross I of t omega of t. So this is basically the F equals ma for the angular motion. And now we can do the same time integration we did before with the particles. And so again, we have a second order differential equation, because this is somehow related with the second derivative of our orientation. So it's quite analogous. Okay, so omega by t times tau t minus t plus omega. So this is just resolved to sigma, right? So this is our angular acceleration. And then we have the time derivative of the orientation is omega star times r of t. And now, again, we integrate over this time step h. Which leads to the integral over the omega equals integral over minus 1 tau minus omega plus. Okay, I'm lazy, I'm omitting the time dependencies again. I hope you don't mind. T. And the integral then now again we assume the torque is constant and also the angular velocity over this time period, and we basically arrive at omega 1 equals omega 0 plus h times I. Now of course I depends also on time, so well we take the inertia tensor at the beginning of the time step. Inverse tau 0 minus and R1 equals R0 plus H times omega 0 star R0.
Is that down below? Is that W2X or is that W?
Oh, sorry. Yeah, it's the star.
Star.
Right, it's this cross product matrix. It's just R dot, basically. Okay, so this would be the discretized, the discrete time integration for some time step h for the angular motion. However, there is a problem with this, and that's this part. Because if you think about it, I mean I had this drawing before where you have the circle, you have some point, and what we do here is basically just add h times this the velocity of this well for a column basically of our rotation matrix R, which is a little vector. So for example, this would be one column vector of R. We basically just add this tangential velocity there. And of course, as you can see, this will also change the length of this vector, right? So like the resulting matrix R1 will actually not be an orthogonal matrix anymore. Because, well, actually, if you implement it like this, you will actually see your bodies grow in time, which doesn't make sense for rigid body simulation. So one way out of this would, of course, to just normalize all these vectors, but then they also kind of get skewed, so they are not orthogonal to each other anymore. So you would also need a re-orthogonalization of this matrix in every time step, which is, well, quite inefficient. And there's a better way to do this. So now, I mean, what can we do to rotation matrices? So the result is also a rotation matrix. Well, of course, that's using a product with another rotation matrix, right? Because the product of two rotation matrices is again an orthogonal matrix. And that's what is also the solution to this problem. So R1 then be some rotation that depends on h times omega. So around some angle phi, and some axis. Well, the axis, of course, is just our omega normalized times R0. So what do we use for this angle then? Well, we use h times omega 0, and the norm of that, of course. So as phi, we use h times omega 0 And well, intuitively, what this does, it just rotates our rigid body just incrementally by this, well, depending on the time step and the angular velocity. So we just need to construct this rotation matrix from a given angle and axis. And for that, there's a formula. It's called Rodriguez rotation formula. I hope you can see it down here. Rodriguez rotation formula. Okay, so this rotation matrix, depending on phi and some axis, let's call it k. That's just cosine of phi times the identity matrix. Let's call it E3. So this is just identity matrix 1, 1, 1 plus sine phi times. Now this is the cross product matrix of k again, plus 1 minus cosine of phi times k times k transpose. So this is not the dot product, but this kind of outer product that where you get a matrix. Right. So yeah, that kind of solves this whole issue with rigid bodies suddenly becoming enlarged.
Did you say E3 was an identity?
Right. I mean, I didn't want to use I because it's the inertia tensor. Maybe maybe people also denote it by ID. But then it's 2 letters, and I don't know. Okay, so I think that's 1 hour, 20 minutes. So we didn't quite get to the strings, but I think we covered the basics. And in the next lecture, I will explain something about articulation constraints, so about joints and hinges and how to actually simulate mechanisms. No context though, that's part of the third lecture. Okay.